Welcome to Opening Voices. I'm Quentin, CEO of Clever Cloud. Today we are meeting with Philippe Notton and Craig Prunty, respectively CEO and VP of SiPearl. SiPearl is a European leading tech company specialized in processor design. Hello and welcome to Open Voices. I'm Quentin and I am traveling around Europe to find a good tech leader and explain what we are doing in Europe to create the new technology and the future. Today we are in Paris, precisely in Maison Lafitte, with Philippe Notton to discuss about SiPearl, semiconductor and stuff. Hi, thank you very much for welcoming me, Philippe.
Bonjour Quentin. Thanks for this opportunity to discuss semiconductor, SiPearl, compute chips.
So first and foremost, when is the year when we created SiPearl?
The company has been set up in June 2019, and the first employee started in January 2020. So we're a bit more than 5 years now.
So it's a company which is 5 years old. Yes. And the purpose of SiPearl is what?
So we are a pure semiconductor fabless company. The motto is to build compute chip, starting with high-performance CPUs.
Okay, so there is a lot of things to discuss that. The first thing is it's a fabless company. Maybe here we can explain a little bit. So first, what is a semiconductor? Is the chips that power IT? What is the difference between a small chip like can produce ST microelectronics and what does SiPearl? Maybe explain a little bit.
So that's the full challenge of understanding what is semiconductor. So it starts with a diode, which is you have 10 diodes per sense, to an NVIDIA H100 on the other side of the spectrum, which is $40,000. And in between, you will have some microcontroller, $1, for instance, that's what ST is doing. You will have some image sensors, a couple dollars. You will have some baseband processors like the one you have in your phone, or something like $100. You will have some semiconductor focused on radio frequencies for transmission, which can be a couple dollars, so it's quite wide. On our side, so what SiPearl is doing, it's at almost at one of the extreme of the spectrum, because we are talking about CPUs, which are, let's say, their value, it's a couple $1,000s per unit in terms of price, but also with a computing power that you will not find in a microcontroller.
CPU stands for Central Processing Unit. It's a kind of it's the computational unit which is in the heart of every computer.
In all cases, everywhere you have a CPU. This CPU is at the opposite of accelerator or GPU. A CPU is generic, can do everything. But if you want to have something very focused, for instance, cryptographic operations or graphical operations or quantum operation, in this case, you need a dedicated accelerator.
What I try to explain at the beginning of the people about semiconductor is there is mainly three kinds of semiconductors for me. One is ASIC, which is a semiconductor which has the implementation of the algorithm inside it. So if you want to change it, you basically need to regrave it. You have FPGA, which kind of programmable ASIC, but maybe you can temper a little bit there. And the one which are more versatile, which are not the most efficient, because ASIC is very efficient, but are the most versatile, and that's the one we build computer with. And the two others are some things we will use as a peripheral and coprocessor. Am I right when I explain that?
I may add another category, which is so-called ASSP, application standard product. So, and especially in the past, where the cost of designing a chip was reasonable, let's say for 1 million, a couple million, lots of, let's say, industrial company were used to develop or have developed their own ASIC to fulfill a very specific demand. So I have a specific operation I want to do. I can give, let's say, 1 million to a service company, and this service company will build a specific chip just for me, which will be fully suited for my needs.
And it's still something that happens? Or
yes, it still happens, but it's just more and more expensive. Because, for instance, if you want to have a very specific chip for a compute need or something like this, for instance, Apple, they have developed their M2 processor, M3 processor, and we may back to this later on.
So it's become more and more expensive, but still ongoing. Maybe we can explain a little bit there of what kind of semiconductor. So if, for example, you have a router, which is the kind of device will manage the network inside your home with your live box as a small router. But on data center, you will have big router on top of the rack and a small switch on top of mini racks and aggregate. You will have a CPU, small one, and a big ASIC to manage the router, and the ASIC will be managed by the CPU, but the ASIC will do all the complicated and very quick stuff.
It's a good example. So you will host the operating system or the specific network operating system on a CPU, which can be a generic one. But imagine that, for instance, Cisco is building this router. It's going to be a router or a switch with 48 ports. I need to manage these 48 ports. I need to develop a very specific chip that will have these 48 IOs, a huge throughput connected to my CPU. But as Cisco, I have the budget, I have the volume, and I have the budget to have designed a very specific chip to manage all this routing. But if I'm a startup, or if I want to build my own router with, let's say, a couple units to produce, it will be completely insane to develop a chip on demand because I will never have the money back.
Maybe what we can explain there is what we call the cycle inside every semiconductor system, and explain what will be the difference between the three. And after we will focus more on the CPU. What is a cycle? What we call a processor cycle or a semiconductor cycle?
You mean at instruction level?
Yes.
So even, let's say, if we go back in time 40 or 50 years ago, where you had some more, let's say, early CPUs, or 60809 or 6502 or the 80 that you may remember, the datasheet was only a couple pages. You had something like 50 or 80 very basic instructions. So for instance, in one clock cycle, at this time, it was something like 1 microsecond, so 1 million operations a second. It was possible to do a very basic computation, addition of 2 8 bits number, so below 255. And in one clock cycle, you had the possibility to do this basic instruction. Now, what has changed is that the instructions are much, much more complex. So in one clock cycle, you can, in some cases, multiply 2 vectors. You can, in some cases, multiply a matrix. And what has changed also is that it's no longer 1 million instructions per second. It can be 3 or 4 billion instructions per second. So the instructions themselves are much more complex, much more powerful, and you do much more per second.
So if you know you will do a lot of the same algorithm, you engrave it inside an ASIC. In one instruction, you will have everything perform. So it's very powerful. But you need to have it like doing all the time, because it's the only way it will cover the cost of this, and you will be Cisco and stuff. And on the other side, there is a kind of instruction you cannot really do inside the CPU, because you don't have the space to engrave everything, and you will have a coprocessor there, and here enter, for example, the graphical card for NVIDIA. That's it?
That's correct, yes. And because if you want to do a specific computation for instance, a matrix computation, it's either you do it by CPU. So in this case, you have all the partition of the matrix computation. You need to do some sum, multiplication, etc. It's going to cost you multiple cycles to do it. Or if you want to do it in one cycle, you need to develop or write a specific hardware to do the matrix computation. So hardware means extra square millimeters in terms of silicon production. So it means extra cost. And if you want to afford this extra cost in your chip, in this case, you must use it. If not, you just carry some spare square millimeters on the chip. You pay it for nothing. So if you develop it, you need to use it.
So basically, the matrix of silicon is the square millimeter cycle, the way you engrave stuff on this, and a good product is a product which use easily every part of the square millimeter, because in a perfect world we can figure out a very big stuff with every operation engraved inside, and it will be simple. But what you say, it will be so expensive that it will never be affordable and will be sustainable for a company to buy it, isn't it?
That's absolutely correct. At the end, it's a product. You need to produce this product, so you have a cost per square millimeter, small chip, big chip. Ideally, everything has to be used. If not, you just carry some dead bodies on the chip and some square meters you will not use. And the more powerful is the chip, and that's what happens now. They are, let's say, larger and larger with more instructions, more computing capacity, and of course, much more power, which is used to manage them.
Okay, so that's the point of view of what is a chip. So SiPearl is more focused on the CPU. So CPU, the CPU landscape is what today? Who is producing CPU, and what is the CPU landscape? And after we will focus on what exactly does SiPearl.
So here we are talking about CPU, advanced CPU. So the one that you will find at least in a server or supercomputer. We are not talking about microcontroller that you will find in your dish machine, which is another.
Yeah. Okay, we will speak about a CPU. We'll go to a computer,
Okay.
Laptop, and server. Okay. Maybe it can be interesting. We cover the laptop, and maybe even this very small laptop with no keyboard you can have in your hand, which is at the end a smartphone.
So let's say the historic player on CPUs has been Intel, complex 86 instructions. Then AMD did the catch up and are now well deployed. That's for the, let's say, x86 ecosystem. And for
when we say x86, what we describe as the x86,
that's the, let's say, so-called instruction set, and that's the way through the software and all the application you have access, or you use some assembly language. You partition your code into very basic instruction like multiplication, addition, shift, vector computation. x86 that let's say the historic instruction set. Other instruction set happen, MIPS, in the new computer business, which is now on the way down. RISC-V, which is one of the important trends, let's say, for the next decade. ARM.
We will speak a little bit about RISC-V.
ARM, which is, let's say, mainly coming from the mobile phone industry, which is now quite powerful, and that's what you're using in data center and in HPC. So that's, let's say, different class of software and instruction set.
And basically, if I have a software who runs on x86, can I take it and put it on ARM?
No. Okay. No, you need to recompile it. The application can be the same, or the user experience will be the same. You need to recompile it because it's targeted to a specific processor. Now, an ARM processor can be compliant with another ARM processor. Same with x86. That's why the code which was working in your laptop 30 years ago, today is still working because it's still x86 instruction set. And Windows did all the tricks to ensure it's compliant. That's a legacy.
Okay. So basically, the whole landscape was, so because like 40 years ago, there was producer in Europe of CPU. There was many people trying to create some CPU and stuff. And at the end, it contract to basically Intel and AMD.
And newcomers. No.
The newcomers
in terms of CPUs.
Let's talk about the market 5 years ago, and we speak in the next episode about the newcomers. So it retracts to that, and everything around the x86.
That's, let's say, up to 10 years ago, it was the case, yes. And it has been contracted, and especially in Europe, due to the cost of development. Because to build complex products, you need lots of money, and to have lots of money, you need investors, etc. And that's maybe something we avoid lately.
And 10 years ago, we start discussing in Europe about the problem that AMD and Intel are American. And we maybe we need some CPU designed, and we will speak about the production a little bit later, in Europe. So that was a huge introduction about what is an instruction set. And I hope it will not lose you. So ask any question on the social media if you have some question about that. And next week we'll continue about the revolution coming to the CPU with the ARM and RISC-V. I'm still with Philippe Notton in Paris. And we are speaking what is about a CPU. So last week we tried to describe what is a semiconductor market, what is a chip, and how we can manage to understand that. So going back to last week to that. So semiconductor market have been brought to life with the CPU, and there was a kind of status quo for, I don't know, 10 to 15 years. And about 10 years ago, it tried to change. Maybe you can explain there what is the change and what's happening on the market like 10 years ago.
In fact, the first change probably happened in Europe. It was Jean-Claude Juncker, one of the president of Europe at this time, said that we need to limit dependencies. With US technology, Intel, x86 were the middle cost time to push for something. At this time, ARM was still in Europe because it was a British company. It was before SoftBank and before the Brexit. They say, let's push a transition from x86 to ARM. And out of this, they initiated multiple initiatives to develop some, let's say, compute expertise in Europe up to ideally chip production.
So at this time, the smartphone era have already breaked up. So it was already a trending system
And given to ARM.
and all the smartphone, like huge majority of the smartphone was on ARM. I know that there was a few try on other architecture, but ARM was making the market. Maybe here we can describe what is the work of ARM. So it's a British company.
Or it was a British company.
It was a British company. And what is the work of ARM? What does it produce?
It's so-called an IP provider. An IP, intellectual property, it's an element of core technology you have to implement in your solution. You can make that, for instance, you're buying a house, you need to have the brick or the tiny elements. You're not going to buy the house as is. If you want to build yourself, you build the different components. And ARM is providing some tiny elements in terms of IP and especially the compute core, which is what we are using in our with our processor, on which you will put all the software.
So basically, ARM give you part of design of a CPU because the big work about the CPU is designing all the way you need to engrave the silicium to have all the logical, what we call logical gate, which is basically the way we design the tiny program of every instruction, isn't it?
Because from a core to a CPU, you have lots of stuff to add. First, in the CPU, you have multiple cores. In the CPUs, you have in your laptop or server, you can have 4 cores, 8 cores, 10 cores. In a CPU with the class, but the one we are building, we are talking about dozens of cores because you want to have multiple VMs working at the same time in the CPU or to extend the computing power. Now, the way you need first to interconnect the core, because a core is computing some informations, but this information after has to be exhausted and transferred to other cores or to the external memory. So you need to have within the CPU some huge highways, or usually it's a mesh network to transfer these informations. And for this class of CPUs, we are talking about a bandwidth which will be higher than terabytes per second. So it's huge, the quantity of data you can move from a core to another core, the core from a memory.
And we're speaking only to transfer the data inside the tiny chip, which is big like that.
Or from the chip to the memory, which is outside, like DDR5 or HBM, which can be in the...
But it is at this proximity of the CPU, just for the people...
Yes, that's very short-term range.
Because a lot of people think when we talk about terabytes about the network, but the problem of data transfer also happen inside the computer itself. And the magnitude of data transfer we are speaking about in the CPU or between the CPU and the memory is way bigger than the transfer happening in the network.
Yes, for multiple reasons. One of them is propagation, because when you want to transfer one information from this side to this side, and if you have 1 meter in between the 2 points, it's 3 nanoseconds to transfer. Now, when you do this within the chip or in between, let's say, a couple gates, you will talk about picoseconds, and that's the way you can, say, have fast compute. And this kind of propagation time, that's one of the limits today, everywhere. There are some theoretical limit, you cannot do what you want. And of course, it adds also lots of power management, because if you transfer too much information for the long distance, it uses much power. So the more compact it is, the better it is in terms of power efficiency. But also, the drawback is that you concentrate lots of power in a small, let's say, in a couple square centimeters. So at the end, you need to exhaust this power to manage it and so there is no free lunch.
Okay, so that's something maybe people need to understand, that the level of velocity of the transfer and the number of the transfer inside the CPU is a huge, very huge number, which is not the magnitude with the memory, not the magnitude with the hard drive or any storage system. And we don't speak about the network, which is absolutely totally different. It's the same kind of stuff, like going from your bedroom to the kitchen and from your bedroom to maybe Pluton, the far distant planet of the solar system.
That's correct, yes.
It's something very complicated to understand, but you need to be very, very quick at this.
Let's say it's at gate level. It's at almost at the atomic level. So it has to be very short distance if you want to compute this.
So ARM is not producing CPU yet. We can say maybe
not yet.
We will discuss the news a little bit later. So it's not producing CPU. It's only providing you some kind of IP and instruction, and it provided to many other companies around the world. Maybe we can discuss what are the companies producing some ARM CPUs in the world.
You have one quite famous, which is we're discussing smartphone at the beginning. It's not ARM, which is developing directly the chip for smartphone. For instance, it's Qualcomm, MediaTek. And them are ARM-based.
And it's a CPU you will find in many Android-based phones.
Yes,
this kind of
at the cost, which is, let's say, consumer level. So you will spend a couple $1,000 to have this CPU with 4-core, octo-core. Now they are used to say that you have Qualcomm, MediaTek, even Huawei in China. Even if this is, let's say, no longer in Europe, they are using ARM instruction set.
As they're producing their own.
As they develop their own silicon, they develop their own phone. That's the example of vertical integration. In the case of Apple, so they produce the phone, but they develop the chip also.
And so Apple is buying to ARM instruction set to produce their own CPU.
They are licensing the technology and the IPs. They are building their chip. Then they have the cost of the chip fully under control. So the chip margin is for them. That's let's say the 3 vertical integration. And what has this started maybe 10 years ago? Now the GAFAM, so the big, let's say, US clouder, Azure, Google, AWS, Meta, they have developed, or they're still developing their own chips.
Okay.
Why? Then they can have the chips really suitable for their own needs. And in terms of cost control, that's perfect. So instead of giving away a production margin to Intel, AMD, for NVIDIA, it's another topic, but for them, they can be very cost effective.
Right. So majority of companies producing chip today are using the ARM instruction set. So it's kind of very interesting that from smartphone, they jump progressively into other devices. So you say in the server, so in Amazon, you will have the Graviton, for example.
Yes, Graviton family, Cobalt with Azure. Yes, because at the end, it's an open system. So you need to be able to load multiple applications on, let's say, on top of the server. So you need an open instruction set, which is the case of what they do. But the main interest for them, I guess, before the instruction set is cost control. And the fact that the chip, the CPUs or TPUs or other accelerator we're building are fully customized for their own needs. Yeah. But they have the budget to manage it. So they can spend hundreds of millions of dollars to have their own chip for them, which is what the European clouder, unfortunately, cannot do because they don't have the volume, they don't have the scale to develop their own component.
And just to be clear with the listener, when we say there is an architecture and you use it, maybe it can hide another architecture. If you take, for example, an AMD x86 processor, the confidential computing instruction set which allow you to have like a secure enclave for cryptographic key or stuff like that is actually an ARM core inside x86.
Inside the big one, yes. And we can have multiple ARM cores inside of big CPU.
So it's really an instruction set and it will spread. Thus, there is another example. So you say that the majority of the phone are on ARM. So there is a huge coming on the server of the ARM. And thus there is another market where the ARM is really present?
Consumer
for the laptop, for example?
Qualcomm is starting, let's say, to ship CPUs for laptop. Yes, MediaTek will capable do it because Windows has been ported on ARM. It's cheaper. It uses less power. So yeah, for laptop, it's given. And what is a laptop today? It's just a big smartphone without the 5G internet.
And maybe another big producer, maybe we can discuss about the M1 from Apple.
Homemade, yes. And if it works well.
And it's ARM too.
It's ARM 2. It's just that they have developed their own core. They're using the same instruction set, so they did much more themselves on the chip.
So they're not buying so much IP from ARM than before. That's it.
In fact, they have licensed an access or the right to use the instruction set. And the right below the instruction set, the core, they can develop it themselves. Now, they have a good team. They have the resources to do it. They have the money to do.
And that's why they are so efficient.
Because it's really targeted, tailored for their own needs.
That's very interesting. So what does SiPearl in this huge market? So you're focused on producing ARM CPU?
On designing, producing on the wrong.
Explain the difference maybe is this the...
So in the say semiconductor industry, you have two categories. You have the so-called integrated device maker. So they have their own fab. So they design and they produce their own chip. And we have the fabless.
So the design and produce their own chip, we can talk about Intel,
ST, for some verticals like sensors, power components. They are designing themselves, they are producing themselves, even in Europe and in France. Samsung, Samsung is quite impressive also because they are no longer only, let's say, designing CPUs, baseband processor, and all the stuff for phone, but they have also the displays.
Yes,
they have the memories. And in a smartphone, you have plenty of memory. So it's really vertical integration at a huge scale. That's for the integrated one. Now it means that for this you need to have the volume, the budget and the volume, because managing a fab is quite complex. And you have the other category which are fabless. And in terms of fabless, you have AMD, you have Qualcomm, you have NVIDIA. So you can be number one and being fabless. You have plenty of other fabless companies.
Is one of them. Fabless is what? So you're just designing the chip?
Yes.
And after producing the chip itself, is made by other company.
So you design it, you own it. It's your own architecture, your own secrets, and you send it to a global fab, such as TSMC, such as Samsung, because their fab is open. Intel, they're also trying to open their fab.
But I see that Intel is struggling a little bit to open their fab.
Yes, because the strength of TSMC since day one is that in terms of logistics, in terms of the way they work, they can manage thousands of products in parallel, hundreds of customers. So their fab has been, let's say, designed for this.
But they never design any CPU. So
it's not their own product there, it's an open fab. So you pay, you have access to the foundry.
Okay.
So in our case, we're designing the product, and after to make it simple, we'll buy our product from TSMC.
But after the product is made by a supplier, TSMC, majority of the time it's TSMC. There is also
in compute in 90% of the case it's TSMC, yes.
And they send it back to you, and then you sell it.
We own it in all cases, and we sell it. Okay. The interest is that whatever is the volume we want, 100 PCs, 1,000 PCs, 1 million PCs, it's their problem. That we manage it. We don't have the issues of managing the fab, which is just impossible for what we are, let's say, doing, because the cost of such a fab, we are talking about $20 or $30 billion. So just impossible. And
low barrier.
So low entry barrier, and that's part why there are plenty of, let's say, political discussions about having fabs in Europe. And a fab like TSMC works because they have multiple customers. It cannot work for one customer. And that's why also Intel is struggling today with its foundry, because they don't have enough Intel products to fill up Intel fabs.
And that draw the accounting of Intel very low.
Because if a fab is not loaded at more than 80%, the fab is losing money.
Yes, because basically fab need to be operating 24 hours, 7 days per week, like all the time.
And fully loaded to be fine-tuned, because there is so-called a yield issue. So if you don't produce enough PCs out of your fab, the yield is going down. To fine-tune it, need to be very sharp in production, really very.
So fab is about to be sure that your whole installation is fully loaded, because you cannot, it can work, it cannot be financially working, even for very high-end PCs, very, very expensive. If you just are not working for like 24 hours a day, but only 12 hours, the cost will not be twice, but will be like 4 or 5 times. Isn't it?
That's correct, yes.
So it's a very complex work to manage a fab. That's why it's not something you do.
No, and we cannot. We cannot. Let's say for financial reason, it will be useless. We won't be able to load it. It's a different business, and that's why, let's say, TSMC, let's say, is so strong.
And you can produce some SiPearl CPU at TSMC because NVIDIA is producing his own GPU.
No, NVIDIA is fabless also. So NVIDIA is producing also in TSMC.
Yeah.
But what's interesting and what we do is that Apple and NVIDIA are use AMD to use the, let's say, new processes. Like it was an announcement a couple days ago about the new AMD CPU that is going to be in 2 nanometer in TSMC. That's very good because they will be the first one. They debug the process, and once will be, let's say in our case, will be let's say a bit behind, but the process will be fully matured thanks to AMD that, let's say, help TSMC to
because to developing this new process will have cost like billions.
It's crazy, and they, of course, TSMC wants let's say, wants a provider with a good volume to debug it, to mature it, etc. So we'll just be, at least at the beginning, a bit behind, taking benefits of the algorithm.
So in this area, what does SiPearl? So you buy some instruction from ARM, you manage to create a CPU which has a good instruction set for the needs you see on the market, and then you produce with TSMC, and then you have a CPU which is designed in Europe, produced in Taiwan, but designed in Europe, which is reducing the level of dependencies we have to the USA, isn't it?
Yes, we can see it this way. So we license some elements, an IP from ARM to have the compute core. We have designed the other elements of the chip, let's say from architecture to final chip. It's and after, as you said, it's made in TSMC. The interest is that we know at 100% what is in the chip. We fully control the code. You can say it's kind of source code. In fact, it's at hardware level, but we control the source code. So we know perfectly. So there, in terms of risk of backdoor, etc., we know what's inside. It does not mean that it's bug free, but we know the let's say we know the content. After it's going to production, a couple months after, we have the chip back. So it will go to a customer on their motherboard, which will be server or supercomputer, like Evident, which is developing the supercomputer for Jolish in Germany that we will discuss later on.
Okay.
But it's not only the fact that we control the content, it's also a question of creating value. Because the design team is in Europe, so mainly in France and Spain in our case. So this value is redistributed in Europe because the engineers will be better and better, and this expertise remains in Europe.
And it's easy for us to meet the SiPearl engineer. To be fair, I spent a lot of time with some the SiPearl engineer because we can discuss low-level optimization, very efficient for our usage, and that can be very financially interesting or environmentally interesting and stuff like that. So maybe about explain what it is. We will figure out next week what have been the roadmap and what have SiPearl does, and after we will discuss a little bit with Greg of the market of what exactly is the position of the market of SiPearl. So thank you very much for listening. Hello. We're still with Philippe Notton from SiPearl, and I'm Quentin Adam from Opening Voices. We are in Paris. We are speaking about microconductor and what we can do in Europe to build a CPU. So in the last 2 episodes, we have the discussion about the market, what is semiconductor, and all the market is structure to produce these so-called chips that allow you to see some nice cat GIF all the time. What we can discuss here, Philippe, is about to say, okay, SiPearl is using license of ARM instruction to build and design its own instruction set and design it, and TSMC is producing that.
Mhm.
So the company have been created in 2019. So it's about like 5 years old now. Today, what is the company size, for example, number of people to design this kind of stuff? What is the number of people you need to do those?
Today we have 5 R&D sites, 4 in France, 1 in Spain, about to open in Italy. We have 200 persons and it's around 150 engineers. So 75% of the staff is R&D centric.
And to design stuff, so you design the CPU, and how do you design it? It's basically a paper and pencil, or it's
on the whiteboard, so it's so easy to do. Now, we first, in terms of R&D, we have about half of the R&D is software, half of the R&D is hardware design. Why software? Because we need guys to develop a Linux kernel, BIOS, and all the components you have in a motherboard. And after, for the hardware, the design of the chip, you have different expertise from architecture, design itself, implementation, which is the way they are going to draw all the tracks and the gates in the chip, and a team which is the one focused on production that will drive TSMC and to ensure that when the chips are back from the factory, they are working perfectly.
Ordering a chip at TSMC is not like just drag and drop a chip and click add on the car.
No, and especially because when you spend a couple $1,000 million for the fab, you are not going to send it as is. So it has to be fully tested, emulated, simulated before to ensure that what you send to TSMC is exactly what you want it to do at the
simulation is something simple, I feel, no?
Yes, also it's so easy. No, it's easy to simulate when you have one gate. So one basic element on the chip.
When I was in engineering school, I do it. I have done my own CPU and simulated it.
Yes.
And you have like 48 gates, something like that.
And now we have 60 billion gates.
Okay, so
all of them are useful.
I assume the software I was using in the time is not the same, isn't it?
No, that's why it's kind of exponential complexity. And the more gates you have, the more complexities, the more test cases you have. And these 60 billion gates, all of them have to work in proper order.
And does there is a market of this kind of software, or is something you need to buy or build yourself or making at home? So what is exactly the number of stuff you need to do inside buying on the market? What is the level of secret?
So if by software, you mean the design software?
Yes.
In French, it's CAO, or in English, it's EDA, electronic design automation. That's all the tools we need to have to design the chip. If you have a writer, you just need to have Microsoft Office, that you will spend it 10 euros a month to have it. In our cases, we have a huge pool of software we have licensed with plenty of different products to help us during the different phase of the design, to design, to test, to emulate. So it's very expensive, and we have guys which are experts in all these tools, because today you don't design a chip, and especially a CPU, without a fully, let's say, a full batch of design software. Plus the data centers we have built, where we push the design, we simulate the design to ensure it.
For example, I know that simulated the design is a complex stuff that you don't do in traditional hardware.
So you can simulate by software. After, if you want to simulate at so-called gate level, it's huge in terms of compute time. We have one of the largest machines in Europe called it's an emulator. It's a rack of FPGAs where we can drop into this rack of FPGAs an image of the chip, and this chip will work at something like, let's say, 500 kilohertz instead of 3 gigahertz. But at 500 kilohertz, you can start the software. So the Linux kernel will boot in a couple hours, just 3 hours in our cases,
and starting to simulate and see how everything is working here.
So Like you will have a shell with you can have an hello world. You will see that the kernel will boot and will not add in kernel panic. It's a good sign. So it means that plenty of gates in the chip has already been used. You can start to have communication over PCI. But now the drawback is that in emulation, it takes time, but it's reasonable. So you can wait a couple hours, or if you send a batch on Friday, on Monday morning, you have the result of the emulation. And with this, you limit the risk because you can fix them during the design phase and not after the production. Because if you fix hardware bugs after the production, it's complex because it's a new spin and lots of expenses to do.
But basically, if you find a bug, you will need to fix the bug, then relaunch the simulation, which means like lowest cost of minimum bug in the design will be 1 or 2 weeks fix just to get the simulation results.
We have some so-called run which can take a couple weeks, but anyway, compared to an issue in production, it's nothing.
And just to understand the feedback loop, because basically, if you're a developer, you just like write a web page, it refresh on the browser, and you have your feedback loop. But there, the feedback loop of something, each about 1 or 2 weeks minimum time. It can be bigger for a bug untangling with memory and stuff. That will creating a long time to debug the stuff, which is elongates the time from an industrial point of view. And for sure, it's way less expensive than producing the stuff, putting the chip and say, oh, it doesn't. Oops. How many of this we have produced? 1,000. Oh, that's nice.
So in this case, this is not an option. Everything has to be tested before. Simulation, emulation. So yes, it takes time, but it's much more reasonable. And that's the, let's say, standard flow now to develop such a processor.
Okay. And so you have this, which is creating the stuff, and you have also other kind of. So when you have this simulator, for example, this simulator is something that you can buy like off the shelf and something, or it's something you need to build up, assemble. Like for example, how Intel or AMD works on this. Does they are buying product on the market, or is this kind of private cooking system they have?
So the competition is not necessarily disclosing its design secrets, but it's not rocket science. We have access to the same design tools, to the same emulator. We just know that in US, companies like AMD, they have 10x or 20x our capacity in terms of computer emulation. So we are, let's say, followers on it, and with different budget, but that's the same. In fact, it's kind of STEM and standard methodology.
It's standard methodology, but it's not very well available in the market. So if you need it to produce this kind of industrial tools, such as the simulation data center you have, and all the software stack and software pipe to produce that, you need to have like maybe 20 to 30 people at home that are just
focus on this, and we learned a lot. Today, our chip, Area 1, the first one, is the largest and the most complex silicon design in Europe. So we had to build this expertise and learn from scratch how to do it. Learn how to use these tools, to debug the tools, to build the emulator, to build our own data center for your compute farms to the tools. Yes, because it's not that we upstream some bug fixes, but there are, let's say, strong and day-to-day discussion with our support team to fix some bugs which happens after on the next release.
So basically, it's not simple to do this.
No.
It's basically a lot of industrial tools you are producing there, and you need more money to be able to have multiple simulation racks, to be able to have many simulation working on the same time on different parts of the CPU if you want to fix faster the point.
In our data center, we have more than 300 servers to help us just to design the chip. But the emulator, which are, let's say, very specific hardware. So all the logistics.
It's a very specific hardware, the emulator hardware?
The emulator, yes, it looks like racks, standard racks, but it's just blades of FPGAs, where you can have in 2 racks, or it's not 2 racks, it's probably 4 racks, something like this. You can have a rare one of a CPU, which is working in emulation. It's the same one, even with its PCI interface. Even the memory is emulated. It's just much more slower than the chip, let's say, used in real life. It's at 500 kilohertz instead of 3 gigs, 3 gigahertz.
And if you have a like magical wand, for example, if you have like 3 times this kind of racks, does it will accelerate SiPearl or not?
Yes, because in this case, you can have more engineers working on it.
In parallel, and go and velocity.
Yes.
And that's basically how Intel or AMD does.
Yes, because they have better capacity. Doesn't mean that the emulation would be faster, but you can have more engineers, so you can use multiple test cases or even start, let's say, working on advanced software on it.
Okay, and today you cannot because you don't have the financing to do it.
We spend already a lot in emulation, so doing more today is just, let's say, impossible.
Okay,
but we are quite happy. You are reasonably happy about this because we have an emulation capacity which is unique in Europe.
And does there is other company working on this kind of stuff in Europe or not at all? So that means that maybe you need to recreate the kind of skills that nobody have here.
That's the challenge we have to. So building such a team took time. Now the guys are, let's say, very good, but we spent years in learning how to do it. It's really when you're creating an expertise from scratch. We cannot, let's say, recruit engineers from US or these places because they don't want to come to Europe. It's going to be also different class of salary. So we created from scratch. We are even involved with engineering school to push the school to produce engineers, let's say, focus on this kind of technology. And here we are in, let's say, long cycle. But yes, it takes time. The pity is that the jobs are fascinating. The product is quite exciting. So but step by step we'll be able to do it ideally. So overall companies like SiPearl should do it also in Europe. That's the way you create an expertise and pool of an ecosystem.
So and companies like maybe Visora that creating a calculation system for AI, which use the same kind of tooling at this point, but it's less complex to do it.
Yeah, it's an accelerator, not a CPU, so it's not exactly the same design, but in terms of methodology, design flow, design tools, yeah, they have access to the same pool of products.
And the SiPearl is maybe the biggest company on the area, so basically you can help other company by driving the ecosystem.
That's the cost of being the pioneer, and pushing the schools to produce engineers, creating expertise, ensuring that our engineers will stay with us. So we need to sell them, let's say, very exciting products. But yes, you're right. We need to develop an ecosystem, such as the ecosystem which exists in California, which exists in Texas, in Austin, which exists in Tel Aviv and Jerusalem in Israel. Today in Western Europe, we are not at this level. We are pushing for it. The engineers are good. They just need the project, and to have this kind of project, they need the money or the equity to build startups.
And if we speak about what does SiPearl, so you are currently on the phase of polishing the design before the production of the first CPU, isn't it?
We are at a couple weeks from the production to fix last-minute bugs and ensure that we'll have, let's say, a very, limited number of bugs in production.
Okay.
That we can fix by software, something like this.
Yes, because at the end you can just kill some branch of the CPU and say, okay, no worries.
Or a software fix can do it. So it's a question of, let's say, risk mitigation. So if you go to production too quickly, you'll have to, let's say, too many bugs at the end.
And it will reduce the capacity of the CPU at the end.
Another way also, yes, if you reduce the clock, so if the chip is slower or you clock it slower, you limit the risk. But the deal is that the more advanced is the simulation, the computation, the emulation, the layout, the better will be the chip in performances also. Just at one stage you say, okay, now we are good to production. We are good for production. We go for it.
Okay. And the CPU. So we will discuss with Craig in next week about the market and where we will use the CPU. Basically, there is other people working on central processor unit for server or laptop in Europe or not?
Not to my knowledge. On acceleration, yes.
On acceleration?
On pure CPU, no.
On acceleration, you have like Visora, you have Spin Cloud.
Spin Cloud is Quantum.
No, they have made a switch to like everyone this year. They have a. You know what? We discovered that our CPU, our accelerator is so good at making LLM working faster. The joke is if you go on some for example like you have open Euro HPC conference for example in Krakow like a few weeks ago. Basically you will have every producer of semiconductor which go there, because even if you're not on the HPC market, this is where you will be able to talk with people about HPC, about semiconductor, about everything. And basically the joke is everyone this year was about to explain how what they do is very good for LLM. Like memory is good for LLM.
That's the next big thing.
There is a lot of sales to do there, and so there's Visora, Spin Cloud,
Accelera in Holland. You had Gallery in Grenoble,
which is also so. SiPearl is a partner of Clever Cloud in many research projects. I haven't disclosed this before, but we do a lot of press release about that. So we work together at this, and I'm very proud of working with that. And I have to say that the engineer I have met in SiPearl are one of the best I have seen in my life.
Glad to hear this.
And very, very interesting to talk with these guys. And what we are working together is very, very exciting. And maybe what can be interesting there is also, so we also work with Carré on DPU. So everyone is knowing each other on the market, but nobody else is working on the CPU. So basically, SiPearl is not making out. We will lose all this expertise we are going to make there, and if we want to fulfill fab in Europe one day, we need all these guys to be up and
you need all the products to fill up the fab.
Yes,
that's why TSMC arrived in Arizona, because they have all the US products. Because they will Qualcomm, NVIDIA, the one from the GAFA that could load this fab. Apple, yes.
So that's why that's how they will load this fab. But today in Europe, you cannot load the fab with Gallery, SiPearl, and Visora.
Not at all. Yes.
It's about like 15% of the fab capacity or something like that.
No, it's below 1%. That's if you take all the startup accumulated in Europe today, it's even not 1% of the fab. It's no, we're not at this stage. You need some huge pipe like Apple. It's huge volume in consumer. The GAFAM, because they are big die, so it's big wafers and let's say good volume. No, today we are not at all ready to have a fab.
Okay, so less than 1%. So that's why we need to work a lot to raise this market, which is a market that nobody understands really. And it's quite complex to explain to the people. And that's why I want to do this podcast, because I think it's very important for the people to understand what we are doing there. So what the future? So in 5 years, you have built the whole industrial stack to design your product and to creating the good connection with TSMC. Yes. Because creating the connection with TSMC was not like so easy. It's not like giving them a phone call saying we have a CPU to produce. I send you the design in a mail like right now, and can you call me back by Monday with a quote?
I need to wire the money also for this, not only the design file. No, to be honest, if you have the money, TSMC is open. There is no free lunch, so you need to pay them a lot for the services. It makes sense. But the way they have structured TSMC, it's open. So you can do it. The pity that today, if you want...
Even if you are producing like less than 1% of the fab...
It's not volume related.
Okay.
It's the access to the technology. Today, producing a chip in 5.3 or 2 nanometer, that's very expensive. 15 years ago, producing a chip in 65 nanometer was much more reasonable. Now it's just a question of scale. And there are not so many candidates to do it. If you have the money, if you have the design team, the money, the product, you have access to them.
Okay.
So it's not that complex. It's much more question of resources. And
I see we are a little bit behind the clock. maybe just in 1 minute. So I'm pretty sure that what you are doing there, it will be a huge success. But if you have 1 or 2 recommendations about what's make you slower and not delivering enough inside what you are building.
Access to human resources. Building a team takes time. You need to recruit the guy. You need to try them, or they have to be self-trained to understand the way to.
Because there is no learning center for this kind of stuff. So people need to read books, go to conference to speak with other professionals, and it takes time to build up the team.
In this segment, yes. If you are in the web business and you are building a SaaS platform, you will find a CTO or VP of R&D that has done this 10 times, even in France. For what we do, it just does not exist.
So you need to create it.
We need to create it. And to create, you learn, you try, you fail, you retry, and at the end, you're good. So this takes, let's say, this takes time. After, there's the access to cash, equity. So licensing of course, you need to pay the guys, but licensing the tools, building a data center, this is over expensive. The access to TSFs, it's over expensive. So the budget spent on a first chip is just completely crazy. We are talking about 9 digits. It's completely insane, the amount of money you have to involve on it. So it takes time to find it. And this culture of risk and raising equity in Europe for semiconductor, even if everybody's talking about semiconductor, but this culture of risk just doesn't exist. So it's quite complex to finance these kind of operations, even if we know at the end we can make lots of money out of it. So say it's not California, it's not Israel, it's Western Europe. So now we have good investors on board, but it took time to find them.
Okay. So maybe we will discuss the market with Craig next week. I have to say thank you, Philippe.
Thanks for the invitation.
The time to explain a little bit the market and what you're doing there, and I hope we will see the rare one quickly soon.
In your data center.
In my data center, it's already signed. So thanks a lot. See you next week, each other. We will continue this discussion about semiconductor. I'm still inside the SiPearl headquarters in Maison Lafitte near Paris. And I'm no more with Philippe, but I am with Craig Prunty. Are you doing well?
Yes, perfect.
And what is your role at SiPearl? And we will continue discussing what we have done the last week and the week before. And we will continue a little bit with Philippe a little bit later. So
Sure.
Explain me what is your role in SiPearl?
I'm responsible for product marketing. So we look at what products the market needs, what are our market verticals, how do we address them, and then how do we build the product roadmap.
Okay.
And then when we build the products themselves, do they function as expected, and how do we go to market with them?
No, we discussed that SiPearl had the goal to create a CPU, and the real one is like in a few weeks will be in production, and we will starting to play with at Clever Cloud in a few months now. What is the market that SiPearl address today?
So if we look at processors, and I've worked in processors for probably the last 20 years. So you have different markets that you address. There's consumer, things like tablets, PCs, phones. There's embedded. This is things like base stations or switches where you have a specific processor that's doing functions in these boxes. We build server processors. So they're very large processors, a lot of cores. They sit inside the servers, which are basically the backbone of the internet. So we focus on high performance computing. We focus on what we call data center. This can be cloud data centers, this can be infrastructure. And we're looking also at the enterprise markets, which is typically banks or insurance companies or people who have their own private data centers on premises.
And what is the kind of, why an ARM processor like the one SiPearl does can be interested from this kind of deployment?
So if we look at server processors, if I get looking at the different markets I talked about for embedded markets, typically this is software that the customer owns. If I look at Cisco switches, they have their own software stack. It's in-house. They might use some merchant stack, some Linux stack or something in very specific kernels, but in general, it's their software stack. They own it. For server, the stack is owned by nobody in particular. It's a lot of open. it's some specific ISB. So it's a very broad stack that's worldwide. So you have to have an ISA with all that code that's already ported to the ISA, the instruction set architecture. And if we look at the instruction set architectures today for servers, there are 3 that are ported enough to be useful to customers. x86, and that's AMD, and that's Intel. PowerPC or Open Power, that's IBM today. The third choice is ARM. And again, it's about the software running on the hardware. ARM is open to anybody who wants to license it, to pay for the licensing. So it's the most democratic solution.
So we already explained with it that there was a lot of users of ARM, like Apple, like Samsung, like MediaTek, and many other stuff.
Yep.
And those there is people making ARM in the server right now, or not at all?
There are many. So, and there's a long history. Calxeda was the first company to start doing this. They were born, they started in 2008. They ended in 2012. There are many companies that started with ARM servers over time, and they were building this software ecosystem. Today, if we look at who's building servers on ARM, most of the hyperscalers.
So Amazon,
AWS,
Intel,
Microsoft.
Yes, with it's called the Cobalt stack.
Cobalt, exactly. Google with Axion.
Okay.
Then we have other folks that have been in this market and maybe back again, like Qualcomm. They bought a company called Nuvia that was doing a bunch of guys that were from Apple previously. Apple has a processor, but it's not really a server processor, at least as far as we know. They're not very open. We know that they're making the M1, M2, M3, which is in their
So the consumer stack.
Exactly.
So basically, if you look at this, I'm very happy because we bring the Apple subject, because people think that creating the processor was a problem for them. If you look at the processor is in Apple is not only the processor; they basically built everything inside it.
Software is so important for the hardware; it drives a lot.
Yeah, but if you look at the chip, inside the chip you have the LPU, the memory. That they basically built everything just to this. And no a motherboard from an Apple device is basically the chip, memory, a hard drive, because they basically mold the hard drive directly to the motherboard, and that's it. And wiring for the plug. But it's basically absolutely nothing.
Designed for manufacturer. Exactly. They're looking exactly what functions they need, what do they accelerate. And the energy efficiency that they have is fantastic. The battery life of their product is incredible.
And from an industrial point of view, the difference between an iMac, a MacBook Retina, a MacBook Air, and an iPad Pro is the aluminum box. That's it.
Maybe a bit of performance, but you're right. In general, it's the same base. Yeah.
So it's very important from an industrial point of view to understand that. So basically, a lot of companies are pushing to the ARM on the server side. Why ARM on the server side is interesting if you compare to x86?
Well, a couple of reasons. Again, one, because you have a lot of different people designing on ARM, so it opens up a lot of possibilities in terms of the software development. But two is energy efficiency, and there's no magic. There's still physics behind x86 and ARM. I could design anything I want in x86. I could design very simple solutions or very complex. Same with ARM. The challenge we have with x86 today is that it's got legacy. And with each generation, they have to be backward compatible to the generation before. So this creates a kind of a baggage, an overhead. So if I look at the performance of an ARM core versus an x86 core, for the same performance, I'm about 30% smaller in size for the ARM core because I don't have this legacy I have to support, because it's a newer ISA per server. So I get energy efficiency by using the ARM architecture that I don't have with x86 today.
If we can design a little bit the energy efficiency for the people listening this, is basically the Apple laptop on Intel was about maybe 2 hours battery life, something like that. With the M1, it's about 8 to 10 hours. We can say for the server, it's the same magnitude order or something like that.
Well, so it can be, but that's not just because of ARM and x86. It's because Apple had a lot more freedom of design with ARM. They built their own processor, so they put in the elements that they really cared about, right? So they're designing a kind of a boutique server for there's a boutique processor, let's say, not a boutique server. So they don't have that freedom on x86 today. That's the big difference. So per se, I wouldn't say that it depends on how you design your processor. What we have is a lot of freedom of design with ARM, and we don't have a license for x86. Does that make sense?
Yes,
Yeah.
it's perfectly.
So it gives us the ability to design what we want to design.
And can we say that the kind of boutique CPU designed by Apple is the same kind of reasons why Graviton or Google are working on this kind of stuff, because they want to design exactly the CPU they want to use, because they benchmark the CPU and say, we basically don't use that, and we pay for it, and it's absolutely nonsense.
Exactly. There's two parts of it. One is that they want to design the processor exactly for what they want. And if you look at Amazon, what do they care about? The thing they care about most is recommendation engines, right? That's really the function that they do best. They're trying to figure out, when people come to my site, what am I recommending to them? How am I auctioning off ads to them, right? Or making sure that they see the things I want them to see so that I can get the biggest part of their wallet share. If I look at what Google cares about, it's search, right? That's the number one thing they care about. If I look at Microsoft, they care about being able to put Microsoft products on their infrastructure. So all of these guys are building these processors to run their own internal infrastructure, and then they're making them available for cloud services as well. It's both. So they very much care about being able to target that processor for their workloads, for their infrastructure.
Can we say it's a kind of industrial optimization there of energy consumption and money usage and stuff? So,
absolutely.
And how does SiPearl sit on this? Because basically, you will be able to sold some CPU to many peoples to be sure that they will use 100% of the capacity of the CPUs or 80% of the capacity of the CPUs to make them more money and energy efficient on what they do, isn't it?
Yes, that's it. It's our target. Now, we have a broader customer base than, say, AWS is focusing on AWS workloads. Microsoft is focusing on Microsoft. We're going to multiple customers, but we do the same thing. We look at, what do you care about in terms of a processor? What are the elements that you're looking for? Most of them are looking for energy efficiency. The performance to a certain level, but overall it's performance per watt per dollar. So how do we drive our processor performance for this? In HPC, it's a little different than cloud. HPC is performance first. Energy matters. It matters a lot. So we look at the different markets and we figure out, how do we address HPC for performance and performance per watt? And how do we address cloud, which is really more driven for operational efficiency? And so we take these different inputs from the different customers and design to these. And yes, doing this with ARM gives us a lot of flexibility in terms of our product line.
And what is the market you target there? Military, cloud providers, big HPC maybe? Explaining maybe to the people what kind of HPC it can be.
So high performance computing, there's a lot of different verticals there. We got our seed funding from Euro HPC joint undertaking, and they actually build and buy machines for Europe, mostly around national centers, and they create consortiums around these national centers. So these guys run tons of different workloads. Scientists from many companies will come and want to run. There's probably a Pareto list of 300 workloads for each of these centers. So we have to be flexible enough to run all of these workloads and perform well. That's the HPC side. And again, it's about performance. For customers in the data center space, yes, there's military space applications, governmental applications, cloud providers for sure in Europe.
Like us?
Yes, exactly, like Clever Cloud. So we're looking at all of these markets. And in general, we're trying to find the best fit in terms of data center and cloud applications, where you're looking for probably cores that are less big, where in HPC you're looking for very much the performance per core. So it's a bit of a mix in terms of the balance we're trying to strike for our processors.
And if we say so, one of the good point is, when the first RIA 1 will be given to test to the guys, basically, if the market grows, as you have fabless, you just like to order a little bit more from TSMC, so you can scale the production like quite quickly, because production as TSMC is so big that even if you like decouple, you make 10 times your order, But for TSMC, it's like nothing.
Exactly. Yeah. So again, this is one of the being.
So right now, what I'm trying to explain to the people is you're sitting is a large potential amount of gold.
Yes.
Very easy to
Yes.
unlock if everything goes well in the next few months.
Yes. And this is so being a server processor company in Europe. We're alone here in terms of doing this. There are many in the Bay Area. There are some in China as well. But that gives us it's challenging sometimes. It's been challenging to raise money in Europe. You're an entrepreneur. You understand that the view of risk for investing in high tech isn't understood as well here as maybe in the U.S. But the value we have is we're alone. So people see that we have access to a market and a sovereign market here in Europe. So partnering with TSMC, it's very important for us today. We don't have manufacturing of the nodes we need here in Europe, but TSMC is an important partner. We work with VCAs, value chain aggregators, to support us in TSMC. We have important partnerships there. These guys all will help us to ramp to production. And they see the value in us, even though we're a relatively small company, because we're unique in Europe. So we have access to markets and Europe that they would like to help us with.
That's very important and impressive. So how can we describe the new moves in the ARM market? So maybe we can explain that. Before, what we have explained with Philippe is at the beginning, ARM was a British company.
Yes.
And now it's no more British anymore. Maybe we can explain a little bit of the history there.
Sure.
So what is a company would try but unsuccessfully buy ARM, maybe, first, to explain this?
There are a few, but NVIDIA was probably the biggest one that was known. So ARM they're a Cambridge-based company based in the UK for quite a while, for a good 20 years, and then they were bought by SoftBank, which is a Japanese company.
First, NVIDIA tried to buy them.
So they were bought by SoftBank.
No, but at the beginning, NVIDIA tried to buy them, but Europe say no. I try to complete the history for the people who don't know the history.
Sure. In fact, SoftBank bought them first, and then they were going to try and buy them out of SoftBank.
Okay. So at the beginning, SoftBank buy them when?
I'm trying to remember the date. Yeah, 2014 maybe, something.
2014.
I don't remember. I have to look. So don't take this as gospel, right? But maybe 2015.
So a little bit more like 10 years ago.
Yeah.
Okay, SoftBank buys them. So SoftBank is a third Japanese fund, third Japanese telco, and very large hedge funds on the Japanese market.
Big investor in tech, absolutely. Yeah, a lot of investment today in AI and in different telcos, and a lot of investment in tech.
And they bought they bought ARM, and basically they let them operating like all they want.
Exactly. They were trying to help them to grow. So they were using their relationships in tech to try and help ARM actually grow. At the same time, they were leaving them free to run their own business. Exactly.
Okay. And then what's happened? So many people try to buy ARM from SoftBank.
Yeah. So there was a point where there was a consortium that was trying to buy them and sort of create a new Intel. And this was headed by Renee James, who's running Ampere Computing today. She had the idea to vertically integrate on ARM the same way that Intel had. She had been president of Intel. She was number 2 in Intel when she had this idea, I think, originally. And that didn't go through. It was fairly quiet in the market, so it wasn't really publicized, but that was the idea. Then Jensen from NVIDIA kind of had the same idea, that I want to buy now ARM and do a kind of vertical integration and have it front end my GPUs, was his idea. And so he could have CUDA on the CPUs and the GPUs.
Which is already doing it, because NVIDIA is producing a CPU also on top of ARM.
Exactly.
And basically, because you have the Grasshopper, which is a CPU and GPU together, mixed for embedded device, we can say like that.
That's correct. So, well, I mean, it's a server processor, but he's putting the two together. So he has the acceleration, the GPU acceleration with the server front end. And then it allows him to actually have a lot of interaction between the two. So for instance, he can do power steering between the CPU and GPU.
And you have also the Grace, which is not the Grasshopper. When we say the Grasshopper, is because you have the Grace core, which is an ARM core, and the Hopper, which is the famous H100, you have heard about speaking about the LLM computation system.
Exactly.
But if you have the two, you have the Grace Hopper. If you have the Grace, we see it for when they have the CPU alone. It's not a very publicized market on NVIDIA.
No, I would. It's certainly not as let's say famous or popular as Grace Hopper as the solution of the two together. But it's a market they're trying to grow on the compute side. So the idea is they create what they call a module, and it's kind of a small daughter card. We call it a daughter card. They call it a module, where you have Grace and Hopper together on the card, and then you have the memory on the card as well. They use LPDDR, low power DDR, and so what they do, instead of putting Grace and Hopper on this module, they put Grace and Grace. So it doubles the CPU compute, and there's no GPU. And the idea is then this is a server processor. It's had some success in the market. They're looking at continuing that with the next generations of processor as well. For us, as a ARM server processor vendor, again, this is helping us to grow that software ecosystem. The more people who are building ARM server processors, the more and more that software ecosystem grows, which means that ARM has a larger place in the market and people are then happy to buy ARM. And this is what we've seen over time.
So for you, it's a good news.
It's good news. The growing ecosystem is good news for all boats rise with the tide.
Which is awesome. So basically, right now there is a new Renee James tried to buy it.
Sure, they did a vertically integrated by ARM. Yep.
And it didn't work. And she created Ampere after.
She created Ampere after.
What is Ampere? Maybe we can explain a little bit to the people.
So Ampere Computing is a company that was developing server processors based on ARM technology, targeting the cloud and hyperscaler market. They was recently announced that ARM is buying
kind of a SiPearl, but on the Silicon Valley.
In the Silicon Valley, exactly.
Just to explain, what was the amount of money raised by Ampere Computing?
3 billion.
3 billion.
Yeah.
Can you remember the amount of money raised by SiPearl?
A little over 100 million.
A little over 100 million.
Yeah, 140, 150. I don't know the exact number today. But
so they have like
less than
30 times more money than you.
Yeah.
And you're still producing some CPUs.
Yes.
That's nice.
Exactly. I agree.
So Ampere, she didn't succeed to vertically integrated ARM, so she created something else.
Exactly.
Very clever girl, Renee.
She's got a lot of experience in the semiconductor arena.
Each time I read something she wrote, I was like, okay, she basically understands everything about the way it will work. So
she was president at Intel. She has to understand the semiconductor business, absolutely.
I think that the most redundancy, I think one of the biggest mistakes of Intel has to not name their president, because I think that Intel will be thriving with Renee James at the top of the company.
Dissecting Intel in the second half in the 2010s, and I mean, there's probably a lot of business schools that are looking at that today. Yeah.
Because really she totally understands the market from a technical, industrial, and marketing point of view. It's very brilliant. So she creates Ampere Computing, and basically SoftBank still have ARM, but they decide to put a little bit more money on ARM, and the breaking news is SoftBank is buying Ampere.
Ampere Computing, exactly, for $6.5 billion, I think. So she did okay.
Yeah, she did
took
okay.
a $3 billion investment and got bought for 6.5. Yeah. Yeah.
I think investors have their return.
I think they're happy.
And so basically, SoftBank is making the vertical integration everyone is speaking about in ARM, and everyone was trying to do. And do you think it will change a lot the ARM market? Because SoftBank will not close the ARM market, isn't it?
I think their goal, in my opinion, will be to keep it open. So ARM has spent a lot of time getting into hyperscalers. And it's a big focus for them. And that's a door opener. These guys are market makers. So if you have that technology in the hyperscalers, that's good for ARM. That grows ARM. I mean, today we talk about ARM quite a bit, but their I think the market share they have is something like 5% of the total server market. It's projected to grow, and it's growing fast, but it's still not that much. So it's a lot of greenfield right now for ARM server processors.
So the ARM processor is like 99% of the smartphone market.
Absolutely.
Something between 15 and 20% of the laptop market, and 5% of the server market.
And if we look at the IoT markets, it's dominating. Exactly. Yeah. So there's a huge market.
It's dominating, but on the IoT, you have like smaller stuff like RISC-V.
RISC-V is coming now. Exactly.
A lot of very, very small architecture you never heard about, like the ST. What is the name of the ST architecture?
I haven't looked at it. I haven't looked at the IoT.
The F41 or something like that. You have also the SP and stuff. But it's to be fair with the listener, like it's absolutely not the same market. Basically, if you speak about IoT and embedded system with the people of the CPU, they just are looking at you with like blurry eyes, and so just like, what does this guy are talking about? Because it's not their job. But what is really the price of the RIA one?
Well, so it's not something I don't know if we published that, but it's on the order of, let's say, 6,000 euros.
So it's a 6,000 euro price. Just to remember, when I was building the maker, the central processor unit of the market is the ST Microelectronic ones, is the F411. It's a chip we have at like 45 cents.
Yeah, exactly.
So it's not the market at all. It's absolutely not the same market.
It's not our market for sure.
And that people need to understand, like, what does ST, Bosch, and all these companies are wonderful, and I will try to have an interview once with ST Microelectronic because it's very interesting, but it's absolutely not the same market. So
agreed.
So right now, what you see that this market will be thriving and very interesting for you.
Yes. Yeah, it's growing fast. So again, we see that the ARM server processor market it's projected to be, I can't remember the official numbers now, something like 30% of the total server market by 2030. It's growing quickly, right? And so we're at a point right now, we're at an inflection point in the market. And with AI now, we're seeing more and more growth and more players coming in, and they can be designing on different ICs. Could be RISC-V, could be ARM, but the CPU part. So accelerators might be any ISA. The CPU part, again, you have to be able to support that software ecosystem. So it's either going to be x86, and again, there's two players. PowerPC, which is one player who's sort of moving out of a lot of markets today, IBM, or ARM. So ARM is well positioned in the ARM in the server CPU market to grow exponentially, and that's what's predicted.
And we speak a lot about RISC-V also. Maybe you can describe what is RISC-V and how you see the market about RISC-V.
Sure. So RISC-V is a let's say an open architecture. It's not open source, but it's an open architecture. Anybody can take the license and design what they want.
Yes, because it's an open hardware group, which is a sub-foundation of the Eclipse Foundation.
Exactly. So it was created in Berkeley. The architecture, the ISA itself was created in Berkeley. It's really interesting for universities to use because there's no licensing fee. So if I'm a student looking at how to design microprocessors, I could take RISC-V and try a bunch of things from IoT processors up to maybe, multi-core, 10 cores, 12 cores, or even bigger if I want. Now, it's a relatively new ISA. It's much newer than ARM, for instance. So I don't have the same class of high-end cores that I have today for x86 or for ARM, but that's coming. So what we see is in universities, it's used quite a lot. Well, if you want to grow an ecosystem, a great way is to get it in the schools, get young people playing with it so that they're familiar with it. It's coming into the lower end, the IoT markets today. And slowly, we expect it to grow up into all markets. Today, it's, again, for server CPUs, it's challenging because that software ecosystem I talked about takes at least maybe 10 years to grow. But
or more.
But on the accelerator side, you might have more luck because you're orchestrated by the CPU. So you don't have to touch all the same elements of that software stack.
And on the future of what does SiPearl right now, you have all the real one will be out on the shelf like somewhere this year, something like that.
And in production next year.
And what is the future of product you can see on SiPearl? What is the goal of SiPearl for the next few years?
So our first generation, we focused on HPC for a couple of reasons. One was we were seed funded by the Euro HPC joint undertaking. So there's an interest in Europe in growing the ecosystem around HPC, and SiPearl is part of that. Beyond that, we want to move into other server markets. So certainly cloud computing. We talked about whether it's on-prem, so enterprise, or whether it's public cloud. We want to move into these markets. So our second generation will focus more on what we call data center. And we will have some HPC offerings there as well. But the other reason we started in HPC is getting into data center, you have to have people have to see your product, understand it, and think, yes, I trust that these guys have a product that works. HPC, people are willing to, as we say, kick tires, try new technology, port code. So it's a good place to start because it's kind of the Formula One of server processors. It's the highest end. And if I can build a Formula One car, everybody believes I can build a Fiat.
And the relation you build with someone which is building HPC is way stronger. So basically, you will have like people. It will be easy to have the people like 2 or 3 big contracts on your setup.
Exactly.
For the year, and they can help you debug. They can help you make the software.
They want to know what's under the hood. Exactly.
And basically, if you give them like 10% acceleration or 5% energy efficiency, they will have their payback of working with you very quickly. So that's a very good market for you to start.
And even beyond this, in Europe, users want to use European technology as well. So they see a value in local supply. This is important too.
It's something that was very important to understand, that many people doesn't understand the way that the infrastructure work. And at Clever Cloud, we are well known for rewriting a lot of stuff and recompiling all the stuff. And that's why for us it's very easy to integrate ARM stuff. And that's what we are doing right now with you. And we have a few research projects on this. But it's something you need to understand is the energy bill we have is so high than a 10% reduction of the, and we're not talking about 10% reduction of the project we're working on together. We are speaking about a reduction of the energy of about like 70 to 80%. So it's a very huge, but even a 10% reduction of the energy bill is something that can pay the salary of like 3 or 4 people working on this. So that's something you need to understand. There is why are we so focused on the low level? Because just a few percent of economy there, it's a huge leverage on the bidding point there, and that can draw the difference between European cloud provider and American cloud provider. Because if Amazon is able to shrink the invoice they have on the Graviton, if we don't do that, they have like so much more margin than they can pay a lot of R&D we cannot. So that's why it's so important, I think, to understand that.
I agree. And that's one of the things we want to bring to data center is, so you have the hyperscalers who have the scale to do things themselves. And we want to work with the providers who are not quite that big to give them opportunity to build more custom solutions, maybe integrating accelerators with CPU compute in a way that it allows them to compete with the hyperscalers in terms of solutions. And having that access to ARM processors, for instance, is part of that. So we see an opportunity also in Europe where people maybe don't have the same scale and budgets to build a custom CPU in-house. We can help them to do something semi-custom, let's say.
And maybe there is something we can discuss to in front of the public. We have a research project with company which is but we have also Visora, which is working on accelerator for LLM. We have Calre, which making the DPU, so it's the data transfer. Exactly. Everything is on the hardware. We have a software assembly production, which is 2CRSI. So we have like the CPU, which is the SiPearl, the accelerator, which is the Vesora, the DPU, which is the data transfer, which is Calre. We embed everything in the server, which is the 2C RSI, and the software stack is made by Vates, and ZDML, which is an accelerator for LLM, but they basically rewrite all the software stack around there. And once I will go to an interview with Steve, but the point is creating an entry-level discussion with Steve will be quite complicated, but we will do it. And you have the clever code orchestrating everything with a few other partners. And with that, we basically have the stack of an hyperscaler. And that's something maybe people need to understand. If we combine all the human people working on this, it's less than 1,000 people. But if you look at Google, for example, there are like 120,000 people working there. So it's something you need to understand. It's a huge, complex industrial stack with all the chain of value. And what we try to do in Europe right now is combine them together. And that's something
we talk about building ecosystems, and making sure we have know-how for the different elements here in Europe, so that we can work together on solutions, and sort of bring many together to make one. Well,
and that's something very important to understand, I think, from there. I hope everything we discussed there have helped many of the listeners to understand the semiconductor market and what we do there. And I hope it brings a lot of understanding on this market, about the production, about how it's made, why SiPearl is doing. And what I try to explain is how SiPearl is doing an industrial capacity that we don't have in Europe before, and how it's very well thinking in the market. So thanks a lot for everyone to listen to this, and thanks a lot, Craig, to be with us.
That's fun.
And we will continue a little bit with Philippe a little bit later.
Perfect.
We're still at Opening Voices on the SiPearl HQ in Maison Lafitte in Paris. So the last subtopics we want to discuss there is there is a breakthrough in the technology right now, which is the AI. So artificial intelligence is everywhere. And when we speak about AI, we speak more about the LLM and a very specific case of using here. And I think we are living a very huge acceleration on the industrial revolution of intellectual prostration right now. So what are the new deployment it comes to for SiPearl, and what you see on the market changing from there?
I'll start.
Let's think. Why not? Lots of things.
So AI first, there are two segments. You have machine learning and inference. Machine learning, there is a big, quite good player, NVIDIA. And this market of machine learning, it's going to be only at the end 20%. So the big stuff, the next big thing, it's inference. Inference, of when you're using ChatGPT, you type your question, that's the inference engine. It will compute the answer. And with the CPU we can be quite good, quite clever on inference. Why? Because we have a huge quantity of memory. We have a huge internal bandwidth. So we have the possibility to store a full LLM model within the chip. And then when you will compute inference, all the data as I/O, data management, all this stuff will remain within the chip. So it's going to be faster. It's going to be cooler with less power consumption. So that's also not what we address.
Just to explain to the people, because we have made a few like NICAN calculation at the beginning of our project together on this. What is the magnitude of optimization consumption, electricity consumption we're talking about there?
We did, I guess, part of your team did some computation compared to what...
It's not raw engagement. It's not just like for the people to understand. Are we talking about the 10% optimization?
More. What we're doing is targeting certain parts of AI. So there's different... AI works in tokens. And there are different kinds of elements you might need to support. So there's time to first token, and this would be respond to things like queries. You give a query, you need a response. You can't wait a day or even 10 minutes or something like that. So These kind of applications are time to first token. Then there are things called average time to token, where you have many, many tokens you need to bring back. This would be like translating a text, where you have to develop a bunch of tokens and come back. It turns out that larger accelerators are better for when you need many tokens, but time to first token, this kind of inference is well suited to, say, processors, where you're looking for a quick response, you want a flexible solution, the software might change over time. So again, a CPU is well suited to this. So we're focusing on specific kinds of applications. For these applications, a GPU is overkill, and a GPU consumes a lot of energy. So when you talk about percentage of gain, again, it depends on what application you're talking about, but it can be, 10 to 100. I mean, it can be a factor of 10x.
Yes, it's the napkin calculation we made with Ziedemann and you was something like 70 times less consumption, like not 70%, 70 times. So it's like a lot of energy consumption we can power up. And what I explain to people very often is to explain that basically right now we put POC in production, but the POC is too expensive from an energy, from monetary, for a lot of question is like way too expensive.
Okay.
And from an industrial point of view, we are going to be on the design to cost model. And I think you are one part of the stuff. How do you see for a long time, semiconductor was totally freeze on the market. It was Intel domination, and we don't talk about this. So it's opened up a little bit again, like 10 years ago. And now we have a lot of company rushing again. How do you see the possibility of the market to continue to open? And how do you see the possibility for Europe to gain from there? Because all of the European startups on high performance semiconductor are less than 1% of the production. So it's ridiculous right now. So how do you see your possibility to grow there? And how do you see the possibility to create an ecosystem?
We may be a bit pioneer in creating an ecosystem. That's what we discuss under Vexation in terms of finding resources, finding capital, etc. But this market, by definition, is open. There is no restriction. Especially if you work on the ARM ecosystem, you take an ARM license. If you can afford it, but you take an ARM license and you can develop a platform. It was much more complex in the days of x86 because it was closed with just Intel versus AMD. Now, there is a big shift from x86 to ARM, and this is open, so we may see much more competition. Now, seeing much more competition compete in Europe, this is going to be tough. That's a question of entry barrier and how much you need to spend to build a chip. For AI, yes, there are a couple of other candidates to do it. Maybe the differentiation will be in the software in this case, because they need to provide a software universe, software ecosystem to do it. And EU is very pushy to enable this. They have, let's say, they can give some interesting access to equity, not sufficient, unfortunately, but they want to enable this ecosystem. They want to create competition. So I said they want the European ecosystem to move from x86 to ARM, and also to enable RISC-V, let's say, beyond 2030, which will be the next instruction set, and pushing for other form of acceleration and to limit NVIDIA dependence.
And the way you are built fabless means that basically, if you need to ramp up the CPU production, if you have orders, CPU production will be like just a few weeks time, just a few phone calls to TSMC.
You need to wire money. No, it's not a few weeks. The lead time, because for the chip we let's say we are designing, there are, I guess, more than 1,000 steps in production.
1,000 steps.
It cannot be done in a couple of weeks. We are talking about couple months. It's more than 6 months from order to delivery. Even NVIDIA, with the volume they have, they can save something like 20% in lead time, but it's not going to be an NVIDIA delivery in 2 months, unless they start or something.
Yeah, you have to forecast.
Yeah, we need, and this industry which works with forecast, and the issue that happened during the COVID, especially for the shortage in semiconductor, is that it was a disruption in forecast. And it works with forecast. So if you change the forecast, don't expect in real time a couple of weeks after to have the order or the volume. It just does not work. But now, to go back to your point, if we have order, if we have the money to manage the order. If it is 1,000, 1 million pieces, not an issue. It will happen.
Exactly. Because there's capacity at TSMC. We have partnerships with them. What we can't do is start from zero. It takes about 6 months for an advanced fab line to go from start to finish. Now we can stage wafers. We can even stock, product after production. But we have to have some kind of forecast in place to do that. So that's what we typically do, and that reduces the time to manufacture.
And how do you manage to do that? Because one of the point is to do everything like that, you need to assemble a team which are already the knowledge and the how-to and maybe the network, the people, So how do you manage to do that in SiPearl?
We work with partners, and we have knowledge in relationships internally, and then we work with partners externally as well for a lot of the operations part.
And if it is for what's related to production, so in Taiwan, then I was in Taiwan last week. We're quite close to the Taiwanese ecosystem. I've been working 9 years in a Taiwanese company. Our CTO is Taiwanese, working in this building. Yes, we have one foot there. It helps, and we need to have a team anyway close to the fab to manage the production, to optimize the production. Maybe at one stage to have some test equipments in TSMC. That's the way it happens also, because at one stage you can start to own some elements, so that some optimization we'll have to do at a later stage. Not at the beginning because it will be stupid, but at a later stage, yes, you can optimize this part.
But what we can say is SiPearl at some point is importing back some of the knowledge and skills in others' market. And that's one of the good stuff you have been building. Yourself are going back from a market who already know very well the semiconductor production. And you try to get back. And so there is a lot of engineer. You basically poach around the world and getting back to the SiPearl team.
We have today 24 citizenships on board.
So it's a very...
From South America to Asia, yes, we just don't have any choice because there is a shortage on the market. We need to find a good expert, and there are still some expertise that we need in next year that we don't have. But we won't be able to create it from scratch, so we'll have to find the good resources. And especially for what's related to production, the experts are in Asia. So we'll have to, or in Taiwan for TSMC, so we'll have to be there.
So what I explain very often to the people is cloud computing is about to be a chain of value, an industrial chain of value. And what I have to explain to the people is when we're dealing with the giants and a company like Microsoft, because there is Microsoft Research, with Apple, with Amazon, with Meta, you have company where the magnitude of people working there are on hundreds of thousands of people. So when we try to do the same thing and people say, oh, you're lazy, you don't do the good stuff, what I try to explain is we need to chain up a lot of value. And that's why huge project like we do together with Clever Cloud, with ZDML, with Vesora, with a lot of EMT, which stands for Mines Telecom School and stuff, with Calray, with Atos, with we poach a lot of people on the project. But even if we take the whole bunch of people, it's 1,000, 2,000 people work together, not the dimension. So it's a lot of value chain. Maybe what can be defined there is how you as a pioneer in Europe of this kind of work, which have not made in Europe, you're still discovering part of your work. We can say that like that. And you try to put your own internal work available for the market. Maybe discuss a little bit about that with the simulation, the data center you have, something to try to explain to the people what is the asset value of SiPearl.
Yes, to design a chip, you need a huge computing power. Question of, let's say, simulation. I said we have 60 billion gates, so you need to measure all the exchanges of the gates and show that what you have in the design or what in the simulation is really what you will have out of the product. For this, we have developed our own data center. We spent close to 20 million euros in terms of data center to have our own compute farm and some so-called emulators, so FPGA
Which is
station.
very specific hardware.
It's for chip design. It's very, very specific. So we have to
You need to rewrite all the software on top of this, recompile. So it's not like it's not installing Microsoft Word on a Windows. It's
no. It's not click and play or plug and play.
You have a full team to manage.
Yes, we have an IT team. We have a development flow team. I did not say that we wrote some software. It was maybe building some scripts to ensure that all the different software could work together. Let's say from design to so-called GDS, that's the final file you send to production. In terms of development flow and data center for electronic design, yeah, we built something which is unique, which cost us a lot. We are still learning how to make it, but we'll prove with the first chip that the development flow on this compute farm, let's say, was a success and unique. And we have been audited on this. The auditor reckoned that what we had is definitely unique. And yes, that's something that could be open to others that don't have the budget or to budget to own it, or just don't have time or technical expertise to build it. It's like what you're doing in Clever Cloud. So just a different cloud business. It's not cloud for, let's say, web services. It's cloud for electronic design.
I think it's quite important for the people to understand that it's a lot of people inside in percentage inside what does SiPearl, because basically it's building an industrial assets that we don't have in Europe before. And I think it's the biggest industrial electronic design facilities we have in Europe.
At this level, for this class of chip, yes. And we have something like 15% of our, let's say, headcount engineers, which are just focused on this, the IT part, so the compute farm and the development flow, yes.
So I think it's quite important to understand that because that's the industrial assets also SiPearl is building in Europe. And it's not saying like, because sometimes I have people talking to me and say, yes, but it's an ARM, it will be all replaced by RISC-V. I say, yeah, but at some point, the industrial assets is the ability to design a chip. If SiPearl want to design a RISC-V tomorrow, the same team, the same software, the same process will be used.
Even more complex. Because here, if you replace an ARM core by a RISC-V core, not talking about the ecosystem, etc., you still have to build a chip around it.
Yeah.
It's not because it's open source that it's free. It's not because it's open source or as risk that you have a chip in 5 minutes. So the level of complexity is the same, even maybe more complex with RISC-V because today it's not packaged. And one of the value of ARM is that it's documented. You have all the test script, the test file, etc., and it works at the end. So the complexity will not change.
How do you see the possibility for the market to evolve? Because are you optimistic about the possibilities for Europe to gain weight on the market or not? Because right now we basically near zero of the market in Europe. Do you think that what you are going to do is pioneering the ecosystem and becoming leader of this ecosystem will bring back some skills and understanding to our universities, to your research center? I know you're working with a lot of research center. Can you describe a little bit like this? How many research center in Europe are you working with, for example?
Research centers and universities. We're actually working with universities as well to make sure that there is a curriculum around the design of processors and specifically large processors. But so in terms of research centers, I mean, we're working, again, this is part of our work through the European Processor Initiative. There are many research centers that are actually part of the EPI as well, which is what we were born out of. But these are potential partners and customers of ours in Europe. So if we look at each country has their national computing centers and research centers. In France, we see, for instance, CNRS, INRIA, in COA. In Germany, you see, for instance, Fraunhofer, and plus large universities in many places. We're working with many of these across Europe, and they're all potential customers of ours on the HPC side as well.
If you can describe your work and you compare to something that everyone discovered like a few years ago, that ASML in Netherlands was a pioneer in the semiconductor industry. And the last time I was speaking with the politic, would say to me like, why we do have this kind of SiPearl stuff? Like, but not putting more money on the ASML. Can you describe a little bit the difference between the two work? Because for me, it's two different kind of work, but from a very high point of view, they don't understand the difference. So can you describe the difference of the two and how maybe you can complement the system?
So ASML makes machines for lithography for improving fabs, for being able to manufacture chips. If I make an analogy, let's say that we're talking about Formula One. Maybe they make a fantastic drivetrain that allows you to shift smoothly and accelerate quickly, but that's only a part of the car. It's a very important part, but it's only a part. We're doing something that's more like engine control, let's say, in the car. They're completely different functions. You need both. And the more elements that you have in Europe in terms of this ecosystem, the more control you have over your ecosystem. So we want sovereignty for a couple of reasons. We want to determine our own values, our own European values, which are around data protection, around a lot of elements that are different than values in Europe, values in the US, for instance, or in China. In some cases, they overlap. In some cases, they don't. We want jobs here in Europe around technology. We want to be able to produce here in Europe so that we can't be blockaded around certain technologies. And we see a lot of that today discussed with respect to the US and the US president. So there's a lot of reasons we want sovereignty here. The more elements you have in the supply chain that you control, the more control you have over the total supply chain. That's why we want sovereignty. So ASML is very important. It's one element in terms of allowing low geometry fabs to exist and perform well. It's a really important one, but it's one of many. Does that make sense?
Yeah. And maybe for the people to understand that ASML is provider to TSMC and TSMC is provider to you. It's more for me like this. So basically it's not the same place on the value chain, which is industrial value chain. So I have to thank you because it was a long time we have together, and I hope we were clear for the people to understand what is the value and how we can push forward the semiconductor industry in Europe. There is another point of the market, which is quite important, is the ability to do not provide the full processor, but only the chiplet. Can you explain a little bit of that?
So if we look at the evolution of processing technology over the last 20 years, you saw single core architectures go to multi-core architectures. Then you started seeing accelerators in the 2010s, things like GPUs. But this is a way to have more efficient compute, but it limits what you can specifically work on. Now and we're seeing over time, for instance, Intel, they were dominant in the market because in their fab cycles, they were ahead of everybody. Now, and this was governed by something called Moore's Law, which is basically saying that the amount of compute that you have, at one point it was every year it doubles, then every 18 months it doubles. Well, this is starting to find limits because we're running into a place where we can't continue to reduce the lithography sizes for advanced nodes.
For physical reasons, that's why it's a law of physics.
Exactly. So we're getting down to such low geometries now that we can't just cut them in half. At least we don't see a way to do that technology-wise. So we're starting to see innovation in other ways. And one of the ways we see innovation is in advanced packaging and what we call chiplets, where we break a processor into smaller and smaller size or different functions, and then we put them together in a package. And this allows us to have more compute and different kinds of compute together to create new kinds of processors. So one of the side effects of this is we make CPUs, but a lot of companies are making accelerators. We could take a CPU chiplet, an accelerator chiplet, put them together in a package. Then take a different kind of accelerator, maybe put that in the package. Now I have a different compute. I could have maybe multiple CPU elements or multiple accelerator elements. So I can start to mix and match solutions. Now, this isn't something that we can just buy Lego bricks today. We hope in the 2030s this will happen. But already we're seeing chiplet technologies built into processors, and it's making more compute, larger compute possible even today.
It's basically all the M1 from Apple working.
Apple M1, AMD EPIC line of processors, Intel's making chiplets. NVIDIA today is resisted a little bit. They have the capability to do, but they're doing something where they're aggregating things on what they call a module, similar to chiplets, but not exactly in package. So we're finding ways to aggregate different kinds of compute, and that'll allow SiPearl, as a European actor, to work with other people in Europe making accelerators to create compute solutions.
Or for example, the data transfer technology like Array with the DPU
Exactly.
can be part of the chipset too.
Exactly.
Or network interfaces or optical interfaces.
Maybe for security acceleration, maybe
Or storage and
Exactly.
So that can be a very huge market, and to be fair, that's why the M1 of Apple is so the M line on Apple is so efficient. Because basically, you have the CPU, which is an ARM, but you have the graphical unit interface, the neural processing unit interface, and the memory, and all linked together, and that's it. And I think the network also is on the same. They built everything on.
And in each case, they decide, okay, do I want to put these in separate chips on a motherboard, or do I want to put them in a package? And what's the efficiency that I have, and what's the performance that I have? This is the trade-off people are making today.
Basically, if you look at the Apple, they have one chip.
Exactly.
One chip, and that's it. And it's become possible because now we can make bigger sized chip, because TSMC have been very good at making. So, because for a long time, you have a lot of mistake on the lithography, and more you have a bigger the die will have a mistake, so you will have a lot of burn rate on the production.
For yield, yes.
Yeah.
And it costs way more. So right now, the number of lithography error is becoming very low, and that's allow some people, like the people of the Mistral chip Cerebras, which is a chip which is wafer scale chip, which was not possible like 5 years ago. It was
It's a bit unique what they did in Cerebras.
It's so expensive. I think we did works. I think we're not we're not allowed to disclose the kind of price in a public figure, but it's if you think that NVIDIA 20 or 40K per GPUs is expensive, it's not the same magnitude.
No.
Because of the burn rate you can have. So chiplet is becoming the future, and what you say is SiPearl is already thinking about how to think on this way of thinking.
Exactly. We're looking at and looking at a number of different elements. So working with different partners, looking at advanced packaging solutions, looking at interconnects, looking at how you want to actually segment a processor into different functions so that you get the most reuse on different functions.
And is it linked to the One API project you built with Intel a few years ago?
So that was more about the software stack in many ways. I don't know what we can say about that. It was done under NDA, but
maybe
it was looking at connecting CPUs and GPUs together. Absolutely. And we've also announced projects with NVIDIA and with AMD for the same reasons. And that's one of the things. We build CPUs. We want to be the Swiss Army knife to support accelerators. So we want to be able to support accelerators with many different companies. We don't build our own. We're not trying to make a closed solution of just SiPearl CPU and accelerator. We want to work with everybody.
If you have a GPU and accelerator at one place, you necessarily have a CPU.
To control it, to orchestrate it. Exactly.
So that was Open Voices. I was very pleased to integrate SiPearl, and we all hope for the RIA 1 to be on the shelf very quickly. You can buy it on your Leclerc very soon.
Leclerc Drive, for sure.
Yes, and with Amazon Prime delivery, isn't it?
I guess maybe we have more chances to rent, or let's say, auditors will have more chances to rent a RIA 1 blade on Clever Cloud system.
I hope so very quickly, and maybe just to buy some LLM execution and tokens directly from there. I think that was an important time to understand what is the value chain of the cloud and how do you wait the IT works together. So thank you very much for welcoming me. Thank you for listening Opening Voices. This was the final part of this series of interviews with the SiPearl team. I hope you enjoyed those moments. Please subscribe now so you don't miss our next interview with European tech leaders.